This is another video for discrete time linear systems, ECE 320 at UMass Dartmouth. And today we're going to talk about linear time invariant systems and the convolution sum. The convolution sum is really important because it says if a system is linear and time invariant, that if I know the response of that system to one input, which is the unit impulse, if I know how the system behaves for a unit impulse, I can find the output for any input in the world, which is a really huge, powerful idea. And we'll explain where that comes from and then how that leads us to the convolution sum in this video. In other videos, I've got examples of how to actually evaluate and compute the convolution sum. So if you're looking for more of an example of how do I evaluate the convolution of two signals, I'd suggest go look at some of the other videos on my channel. You can find examples of that, both using the formula itself and using sort of a graphical techniques called flip and shift as well. Okay, so again, today's topic, LTI systems and convolution. Switching over to the whiteboard here. And again, a very important idea is that if I have a system which is both linear and time invariant, which is what we abbreviate as LTI, if I know the input, how the system responds just to this one special input, that is the unit step, or I'm sorry, the unit impulse, I know the output of that, h of n, which is called the impulse response. We call h of n the impulse response because it's how the system responds to an impulse. But this is a hugely important piece of information. The impulse response completely determines the behavior of the LTI system for any input x of n, which is to say I can find the output for any input if all I know is h of n. And we'll see where that comes from, how we get an equation that tells us how to do that in a second. But just before we get to the equation, think about what a huge, amazingly powerful thing that would be if I could do that in real life. Imagine if I could listen to you play just one note on a piano and predict what you would sound like playing any piece of music for the rest of your life. Or if in a sports arena, like if I watched you take one shot in a basketball game and I could predict how you would respond to any situation, any shot in any game for the rest of your life. That would be hugely powerful. Or if I watched you answer one homework question in this class, I could predict your performance in the rest of the class based on that. All those things are obviously not possible in real life, which is to say real life is rarely linear and time invariant. But in the world of linear and time invariant systems, we can do that. And that's why LTI is so important. Those two properties of linearity and time invariance are so important, because if we can prove a system satisfies them, we have this hugely powerful tool of convolution to say, well, now I can say how the system will behave for any input or output. Okay, so where does convolution come from? Wrong color there. Well, it's basically just starting with what we had there a second ago and then building up on the properties of time invariance, linearity and time invariance. So again, I have my LTI system. We'll sort of build this up one piece at a time. We'll say, well, what if instead of just putting in delta of n, suppose I put in an impulse delayed by k. Well, then time invariance tells me the output would also be delayed by k, right? Time invariance says if I shift the input by k samples, I shift the output, which in this case is h, by the same amount. And say, well, what if I then took that delayed input and I scaled it by some amount? Let's call it x of k. Well, linearity's scaling property says if I scale the input by some constant x of k, I have to scale the output by the same amount. And say, well, what if I took a whole bunch of those and added them up? And if I took at all different values of k from minus infinity to plus infinity and added up the inputs, well, again, time invariance says, or sorry, linearity's superposition property says if I sum a bunch of inputs, I take the sum of the corresponding outputs. Well, if I break this equation down, it says I've got a whole bunch of shifted impulses, each scaled by the height of some signal x of k at that time, and I add them all up. This is just another way of writing x of n. right? I can write any signal by thinking of it as a bunch of scaled and shifted impulses all added together. It's almost sort of a circular definition there. And so what I have on this side is it's saying the output y of n is equal to this sum that involves the input and the impulse response for any LTI system. And we call that, in fact, I'll rewrite that here, that we say y of n, it's such an important equation, I'm going to rewrite it. The sum is k goes from minus infinity up to plus infinity of x of k, h of n minus k. Again, we're, just to remind ourselves, this is the input, and the h is the impulse response. That's such an, I don't do this often, but it's such a huge equation in this class. I'm going to put a red box around it. There's some messy quadrilateral, at least. That might be generous to call that a box. But this is what we call the convolution sum. And another way we can say that is the output. Oh, and an important way, we often, just for shorthand, use the star. We say that this is h of n asterisk x of n. So the output, to summarize what we just learned, the output of an LTI system y of n is equal to the convolution of the input x of n with the impulse response h of n. And so that's a hugely powerful result. Like I said earlier, it says you give me any input you want, x of n, I can evaluate the sum. I could write a computer program, because that's just a lot of multiplies and adds to do that. And in fact, a lot of real-time DSP hardware, that's what it does, is they're really fast multiply adders. But if you give me x and I know h, I can tell you what the y will be for any input, any x you want to give me, by just turning the crank on this sum. And I'll go on the next page and say there's sort of, in practice, how do we do it? There's a couple strategies for evaluating it. Strategies. These are strategies for evaluating the convolution sum. Right, and the first is for sometimes we directly evaluate the sum. Right, we just plug it for certain kinds of signals. It's easiest just to plug in the definition of the signal and then use our expert knowledge of infinite series, finite series, and things like that to get a closed form for the sum. And this is often the case, and sometimes the only thing you can do, if x of n or h of n is infinitely long. So something maybe like an exponential signal. The other approach is sometimes called the flip and shift approach, which is a graphical form of convolution. And this works best for finite length signals and impulse responses, because it's sort of a mechanical process to go to. And just as I'll say a little bit more about that again, if we think of the convolution sum, we said, well, I've got x of k times h of n minus k, but we saw earlier in the semester I could also write that as k minus n. So if I'm thinking of the stuff going on inside the sum, it's saying, well, to find the output at some time, say n equals 17, I write x out as a function of k, and then I take h and I flip it, then delay by 17, right? We saw that this n minus k thing is like a flip. if I've got it the other way, this way around, I've got k minus n in terms of, if I'm thinking of this as a function of k, because I'm summing over k, right? So it's saying I take h, I flip it, then I shift it by the n to the sample, the output I'm trying to find. So this is the flip, then this is the shift by n after I flipped it. Then I multiply it together with x of k, point by point. At each k, I multiply them together, take the result of that product, and add it all up. I'll show you, there are other example videos I've already recorded. You can see where, how this plays out, both if I want to draw the signals to help me flip and shift them, and then a slightly more efficient way to do is say, well, all that really matters about the signals is the sequence of amplitude. So I write it out in something I call the ticker tape method. Okay, so that's where the convolution sum comes from and the two main ways we evaluate it. That's all for this video. I'll see you next time.